So here is the beam. It has a concentrated load here, concentrated load here, concentrated load here. It has a concentrated moment, and it has a distributed load. Remember, I had the beam in class the other day, right? So when we were looking at the beam, what are we trying to do? Okay, find the page. Number 2. Oh, it's not, you don't even need that. Okay, we're just looking at the whole problem. I'll point to you when you need to look. So in the shear embedding moment problems, you have a beam, right? And you're trying to calculate the shear and the moment at every single point, so you can decide how big a beam you need and how strong it has to be, right? So what are we really doing? We're really cutting the beam mill location. So if in this section right here, remember we called this section 1, and this section 2, and this section 3, if I wanted to find out what's going on in this section, I have to cut it right here. I'm cutting my beam to find out what's going on in this area right here. So what you wind up doing, this is the math part of the shear embedding moment diagrams. But we could have done it all by hand graphically, which we already did. But I'm going to draw it now. So what I'm going to do is I'm going to cut this beam. I'm going to put the 18 here. I'm going to put the 5 here. I'm going to put the 15 here. I'm going to put the 1,000. So this is pounds, pounds, foot-pounds. We have 5 feet here. And then right here, I start a distributed load. And we don't know the distance. We're going to call that x. Okay? Because I want to know what's going on right here, what's going on right here, what's going on right here, right here, right here. And anywhere along here, I can figure out what the shear and the bending moment diagram is. If I put this up, it's just going to fall down again. That's surprising. So we'll try it. Okay? So I'm trying to calculate. So does everybody see I drew everything up to the point where I'm cutting? And this point right here is the cut point. Everybody see what I did? Right? I drew everything to the left of that cut point. But what I'm trying to, what I'm trying to do is I'm trying to calculate the shear and the moment here, right? So the sign convention, to get the drawings that we want, which we got, the sign convention is to put the shear going down and put the moment like this. So what I'm doing is at the cut, I'm putting, because I'm cutting it, I'm putting a shear force and a moment force so I can calculate what the shear and the moment is at that point. Okay, so now if you want, you can look at the page. So go to problem number 2, which is on page 2. Look at page 2. And if you go down to where it says section 10 to 20, the section that goes 10 to 20 feet. Did somebody else walk in? Andrew, could you just see Andrew? Thanks. So if I wanted to sum up my forces here, sum of my forces in the y, Kyle, what's my sum of my forces in the y? 1,800 minus 15.
And then the distributed load.
Oh, we didn't write the distributed load. 250 pounds per foot. So 250 times x, because x is the distance. And then what else do I have in there? V, and it's a negative, right? Equals 0. So it comes out to be 300 minus 250x minus v equals 0. So v is equal to 300 minus 250x. And if you plug in x was 10 feet, right? So if I plug in 0, I know what the shear is. If I plug in 0, shear is 300 at this point. If I plug in 5, at this point, 5 times 250 is 1250 minus 300, 950 negative. Anyway, if you plug in the values of x, you will get the shear diagram that you wanted. So now let's do the sum of the moments, and I want to do some of the moments about the cut right here. So Paul, what is it? 1,800 times?
It's like 10
plus x, positive or negative?
Negative.
Negative what?
Negative what?
Oh, sorry.
So
Okay, keep
foot
going.
pounds, but okay. So, and then you have it's like you have a positive 1,000.
Right, positive 100, 1,000. You do put in positive because it's positive.
Right.
And then 1,500 times
Oh, okay, so 1,500 times 5,
plus x,
and that would be
positive or negative?
positive.
Positive. And then
And,
250
250 times x.
times x, that's the force, right?
Right.
And what's the distance?
Whoa. The distance from.
Measuring the distance from here.
Um,
What's the center of a rectangle?
oh,
What's
so it's
the
x over
center?
2.
X over 2.
Okay.
And plus m. Right, so that's negative 18,000 minus 1,800x plus 1,000 plus 15 times 5 is 75. 100 plus 1,500 x, oh, I forgot to put the positive. Is this positive or negative? Positive. Plus 125 x squared over x squared plus m equals 0. And what does m turn out to be? Somebody, Haley, could you read it to me on that sheet?
Negative 125 x squared plus 300x plus 900.
So this is all the math. You could do this. This is maybe a little bit new for you, but you could do all this. Do you have to do it? No, just do it graphically. But now you have in your hand the mathematical way of finding the shear and bending moment diagram for all 4 of those problems that we did the other day graphically. So I didn't want you to leave statics without knowing how to do it mathematically. So here I have it for you, but graphically is fine. Okay? In the packet, this is really cool, and you're going to see this again. Let's go to the packet.
Joanne?
Yeah. Did you not get one, Chris?
No, I did get one. I was just
No, I'm
wondering.
talking this
Oh,
Chris.
this Chris. Too many Chris's. Okay. So that moment is positive, right? Because of the right-hand rule.
Yes.
I was just. I
Okay,
mean,
so
I can.
let me say this, and usually when I say it, 10 people won't get it. And it's not so much that you get this part, and that's why I was thinking of leaving it out. But let me say it anyway, okay? And just everybody keep your ears open, okay? When I put a negative, the shear in a negative, and I put a negative v in the equation, v comes positive to the other side, and v is totally equal to this stuff. Which means, by putting v, having a negative sign convention, on the shear and bending moment diagrams, on the shear diagram, when 18 goes up, when 18 is up, the shear diagram goes up. Nothing happens. When it gets here, 15 goes down, it goes down. The direction is going to follow because the sign convention for v is putting v down. If I take an equation and I subtract v, v is going to be brought to the other side, and v is going to have the same sign as this. That's why when we do the shear diagram, we follow 18 up, 15 down, etc. Got it? Okay, but look at the sign convention for the moment. The moment is in the positive, which means everything that's happening here, when you add in the moment is going to be equal to the negative of this. And the reason that this is the correct sign convention is, remember our little cheat sheet? On the shear diagram, if we have 18 going up, and then it comes down to 15, right? This is the area, and it's a positive area. If it's a positive area, we want a positive slope. But in order to get a positive slope, I have to have this as the sign convention. If the sign convention was opposite and v at the cut was positive and the moment was negative, what would you say about all the diagrams we're making? they would be flipped. So in statics, which is what we're learning, this is the sign convention. And this is chosen so that when the load goes up, the diagram goes up. Load comes down, the diagram comes down. When you have a positive area, you have a positive slope. So this is the sign convention. But I remember when I was a student, so I was a civil engineer, I might have seen this 3 times, not 2. You were mechanical, maybe you only see it twice. I don't remember. But I remember having different sign conventions when I went from one course to another. Okay. This to me is the best because it's following it and you don't have to think about flipping stuff. Okay, but you're going to see this at least one more time, And everyone sitting in your class at the university who went through statics there, they're not going to even know this stuff. I'm telling you, you're going to do circles around them. Yeah.
Yeah, so I understand what you're saying about the sign convention, but I guess I'm just kind of confused because yesterday when we did that packet, we had that problem too. This is what I was looking at. Like we went down when we had.
Yes. Okay.
That's what's confusing me because
Yeah,
this would
right,
be positive.
Right.
I
So
would think.
that is the only thing we ever learned this whole semester that is the way we would not think it is.
Okay.
Right. So that is the
Exception.
The exception, thank you, to everything we learned. So just remember it. But here, it's not the exception, right? But remember that if you're adding here, if you're adding this, all this is the negative stuff, right? So that means if you have a positive moment, you got to do the opposite.
Okay.
Because if we have this, if you say positive 1,000 plus m equals 0, m is going to turn out to be negative 1,000. Did you just hear that? Because you looked
Can you
back
say it
down.
again? No,
Yes.
I'm trying to think. Okay.
So you got
1,000.
positive 1,000
Uh-huh.
plus m is equal to 0. M is going to be equal to a negative 1,000.
Okay, that kind of makes sense. Yeah, I
Okay.
see that.
But it is just the exception. We've never had any other exceptions ever
Yeah.
in this class.
Okay.
Mark?
No.
Oh, okay. Okay, so now I think you're comfortable with